if the only thing you get out of this at the very end is you realize that everything you thought you knew about virtual machines and containers is wrong, that'll be a good outcome. That's all you need. So first off, what do I mean when I talk about secure isolation? There's, hundreds and thousands of facets on security, so I am not talking about every facet of security. What I'm talking about here is, start up with one concept. So you have a machine, and on this machine you have a host OS image, that's like bare metal install, and within that you have a collection of guest OSs, which are either containers or virtual machines. So there are an array of different ways that these virtual machines and bare metal machines talk to each other. You may have the virtual machine or container talking to its host. You may have virtual machines or containers talking to each other. They may be talking to other ones on another machine. They may be talking to something out in the cloud, the world around outside them. Now this is a simplification because in real deployments you will tend to have not one or two machines, but these days you'll tend to have hundreds or thousands or hundreds of thousands of machines, all connected either within a data center or across many different data centers around the world. So this is great, right? Communication channels, this is what we want it to do. You have your REST APIs, you have your standard interface from the container or virtual machine to the host. Brilliant. The problem is, for every desirable communication channel between those virtual machines or containers and their host machines and other host machines and other virtual machines and containers and the outside world, there are also undesirable communication channels. And a large part of security today ends up focusing on trying to figure out how to lock down these undesirable communication channels. I'm not going to talk about all of them. There are far too many. I'm not talking about firewalls. I'm not talking about network restrictions. What I'm focusing on is these channels. So the desirable and undesirable channels between a virtual machine or container and its host. So for example, through the hypervisor that may have a security vulnerability, or between one virtual machine and another, one container and another, and within the same machine. So I'm not talking about connections across different machines. So you can narrow it down to a fairly small set, a securely isolated process running on a kernel containing an OS image. And the pop quiz question is that a virtual machine or a container? It's both. Yes. So even though the implementations of virtual machines and containers are quite different, there is a level at which, especially for security considerations, it's actually valuable to consider them together as one set in a slightly more abstract view. So that's what I'm doing. So part of my work over the past year, I'm a PhD student at the University of Cambridge, has been this thing that I call libkvm. So it is a lightweight hypervisor library. So instead of the big bloated QEMU, throws that away, but keeps KVM, which is a kernel module, which is really only hardware virtualization. So it keeps that interface to the hardware virtualization through the Linux kernel, implements a Rust library that then allows various different implementations of hypervisors. You can actually combine it with existing implementations of devices, like virtual devices, existing implementations of virtual memory, and create a variety of different hypervisors out of it. So I chose Rust for memory safety and also for compatibility with C. So what do we mean by memory safety? So there's a class of security flaws, very common in C++, that permit undesired access, specifically because of bugs in your code, flaws in your code, that misuse memory, or you don't directly intend to misuse memory, but through user input or other accidental alterations, allow malicious users to misuse memory. So there's really two classes of these sorts of memory errors. One is spatial errors. This paper, I can't pronounce his name, Cezek-Keres, they use these terms, and they're actually really helpful for mentally distinguishing the two kinds of errors. So spatial errors are errors where the memory has been allocated. The object you're trying to access is there, but through some means in the code, you're accessing some aspect of it that you're outside of the space, the memory space that was allocated for that object. So out-of-bounds pointer, buffer overflows and underflows, stack overflows, things like that. The other side is temporal errors. And these are errors where you have a pointer to a region of memory, and either that pointer to your object, either that memory block hasn't been allocated yet, so your pointer is just sort of out there, and it's not pointing to, or the object was allocated and then freed, but you still have a pointer to it, and so you're accessing a piece of memory. So it's like, it's either before or after the thing exists. It's a temporal error, but you still have a pointer to it. And that allows you to do nasty things in terms of accessing regions of memory that you weren't supposed to. So the thing to know about memory safety, it is not a silver bullet. It does not solve all security flaws or vulnerabilities out in the world, but it does eliminate a class of vulnerabilities, which is useful. Very specifically, it doesn't do anything for vulnerabilities like Spectre and Meltdown. This is sort of a new set of vulnerabilities that they don't require, you don't have any flaws in your code whatsoever. Your code is perfectly well formed, the hardware is functioning as it should, only unfortunately, the way the hardware should function includes some nasty little backdoors where you can get access to regions of memory you aren't supposed to. So, just so you know, memory safety is not everything, but it is useful. So Rust is it's a moderately new language. It's about 10 years old, actually. It only had the 1.0 release fairly recently, but they were very conservative about when to call it 1.0. So, a bit of history that might be useful to know. Where Rust started is Firefox was having trouble with a lot of memory safety vulnerabilities, security flaws. And so some of the developers at Mozilla decided to start experimenting with what would it take to sort of like completely eliminate these from the browser entirely, and they came up with this language, Rust. It is partly used in Firefox now. Not all of Firefox uses it, but some parts of Firefox are now written in Rust. So, Rust memory safety, its features are a set of compile time checks. So when you try to compile your code, it will stop you dead if you perform a certain class of operations that lead to these memory safety flaws. It's based on a concept called linear types that was created for functional languages in the 1990s. But it's a much more practical and usable approach than the original idea of linear types was. That's part of Rust's advantage, is being both practical and theoretically strong. So the way Rust implements them is these concepts of ownership and borrowing. So each object, your little block of memory that's an object, can only have one owner at any time. And that's one of the ways it guarantees that you don't have like multiple pointers and you accidentally free them when you didn't intend to. And then borrowing is when you do create a reference to it, but it knows the difference between the owner and the reference. And it also has this distinction between mutable and immutable references, what it calls borrows. So there can only be one mutable reference to any object, ever, only one. It will give you a compile time error if you do anything else. But if you want to have a whole bunch of pointers to your object floating around, they have to be immutable. So they can't modify the object, which helps avoid that sort of like again, it helps avoid that freeing when you didn't intend it to be freed. It gives you a set of control over when the memory is freed, when it's allocated, who owns it, who can do what with it. So what I found, I've been a C programmer for 30 years, right? So I love C. I'm addicted to C. But what I found in Rust, doing some real serious implementation work in it, is it's actually really nice for rapid prototyping. Because when you're just slamming through a pile of code, you do not want to be, I have done this before, like written a class assignment compiler in C because I didn't want to do it in Java because I hate Java, sorry. And I just got bogged down in like null pointer errors and like all these weird memory exceptions because I was in a hurry and I didn't want to like carefully think through every single memory access and allocation and free in my program. So it's really nice for that because you write some code, you compile it, oh, ugly error. Oh, I'll go, and it tells you the exact line, it tells you what you did wrong and how you need to fix it. It's very helpful compiler errors. So I found it really nice for that, actually. But on the flip side, what's useful for rapid prototyping is also actually useful for long-term maintenance, because if you have a body of code that you're using for a long time with a bunch of people working on it over time, it's in the same way that a lot of big open source projects will add like linters to their gate checks, or certain requirements that you pass certain integration tests before they will merge your patch. This is like a step further. Like the compiler simply won't allow you to do certain stupid things with memory. Again, it's not everything, but it's kind of in that level of a linter or some integration tests and things like that. It gives you a certain level of cleanliness to the code you develop over time. So because Mozilla had a large body of C++ code that they wanted to improve without throwing it all away immediately, they built Rust to be compatible with C at a very low level, so that you can sort of carve out pieces, write them in Rust, like when you have like critical memory safety sections. So some of the ways that it does that, Rust's machine type, constants and variables, are in fact directly memory aligned with C's low-level variables. So if you have a body of Rust code and you define a variable or a constant in it, and then you make a call out to a C library, here I'm calling out to the libc IOCTL library, which is necessary for talking to KVM, because KVM uses the IOCTL interface for all of its communication with user space. So this is a constant, which is actually also defined in the C header files for KVM. But I've defined it in Rust, so I can cleanly define it in Rust. I know that it's safe within all of my Rust code. But then when I come to a point where I need to talk to the C code, I can just pass that variable directly into a C function call. I don't have to do any kind of special magic to convert it to something that works in C. And Rust also knows, with the memory safety checks, at that point, I've passed it into C, and either that's an immutable borrow, or that could be mutable, but if so, you have to pass ownership to the C code, and then the Rust code knows it can no longer modify it. So you have certain safety guarantees on the boundaries between Rust and C as well. Rust also has the ability to find structs that are directly aligned identically to C, so you can pass them, much like the low-level machine types, you can pass them into calls to C functions. This is one, again, the lower struct. This is a struct that is defined in the header files for KVM. And when I have my Rust code that wants to interface with it, I just define exactly the same struct in Rust. And I add this little repr tag at the top that says, I want the C representation instead of Rust's native representation. And Rust knows, so you can use that within Rust as a normal struct, as you can with a Rust struct, but then you can also pass it directly to C, and it has exactly the same memory alignment. Another neat feature of Rust, you can also create a library in Rust, and when you give it a certain set of flags to it, you say this is extern and publicly accessible, and no mangle, so it doesn't like do anything special with the name of the function. It just keeps the function the same, the name of the function identical. Internally, Rust does some function name mangling. So you give it a few tags. In your package definition, you tell it to compile as a dynamic library. That's just a one-line entry in your specification for that build. And what it produces at the end, instead of a Rust native library, is a .so shared object library, which can be used directly in C, or from languages like Ruby or Python, or any language that does the foreign function interface to C can use these libraries directly. So you have your sort of bubble of memory safety within Rust, or high-performant code that you didn't want to write in Python or Ruby, but then you can use them directly in other languages. So this paper that I mentioned before, Sisakeres, talked about, so this was a paper about, it's called SOK, Systemization of Knowledge, the Eternal War in Memory. And it was talking about these C problems with spatial errors and temporal errors. And one of the things they talked about is there are, in fact, a lot of C approaches to fixing these memory safety problems. But most of them, some of them have certain disadvantages. Either they perform very poorly, or they require you to rewrite your entire code base in whatever magical other dialect of C they've invented. And they talked about one of the advantages for adoption for fixes to C memory problems is to make them modular in the sense that you don't have to rewrite your entire code base. You can just rewrite a library and sort of like gradually over time shift over to something that has more memory safety built into it. So this is the compatibility we see is actually good potential for Rust, because you can in fact build your Rust code on top of existing C standard libraries. You don't have to rewrite libc, and also you can replace chunks of your C code, like those critical pieces where you know they're at high risk of memory safety flaws. You can replace those chunks with Rust and have a very tightly controlled interface to the rest of your C code that protects that chunk from C's inability to really lock down on memory safety. So I'm going to shift gears a little bit. We've talked about Rust, but I want to kind of talk about the wider context of secure isolation, kind of how we got where we are and where we're likely to end up next. I don't expect you to memorize this slide. This is just to kind of give you a sense of how far back the concepts of virtualization and containers go. So, in the beginning, in the 1950s, the vast majority of, actually all the machines out there were batch-oriented. So when you wanted to run a program, you load it in through your little like punch cards. The machine would load that into memory. It would run your program all the way through from beginning to end. When it was done, it would clean up, wipe all the state, and start over, right? Brilliant. So, very secure. In the late 1950s, they had this idea that they initially called multi-programming because they called them programs. They didn't have the idea of process yet. That came about in the 60s. So multi-programming was the idea that you might be able to have more than one program running on your machine at the same time. Wild! You can also call it multitasking. So this was initially not multiple processors. Initially, it was just, oh, you could kind of do some multitasking. You can do some context switching between them and kind of run them at the same time. But then very soon after, they came up with the idea of having your I/O processor as an independent unit, so you didn't have to like completely stop all processing on your machine while you were waiting for the user to type that one character. and multiple CPUs. And that followed pretty quickly along after the idea of running more than one thing on the machine at the same time. So here's the tricky thing about having more than one process at the same time. If each process has total control over the machine, I mean, that was fine when you only had one, but when you have two, then suddenly each process has to know what the other process is doing and like have all the intelligence in it not to trample over the other process at the same time. So 2 is complicated, 3 is more complicated. 10, that's like, it starts to become a combinatorial explosion for each process to correctly use memory and not trample over the state of the other process. And it becomes very complicated. And not just complicated in the sense of the code becomes complicated, but just getting a programmer to think through all the implications of the code they're writing in their one little program because it's like interacting with all these other programs. It's really not pleasant. So they came up with this idea that we now know as kernel isolation, which is you create one very privileged process that runs on the machine. You could call it, it was called the supervisor often in the early days. So it was the all-powerful process. And this process would handle all the memory allocation and interrupt handling and like all those really complicated parts for coordinating between like the CPU scheduling, coordinating between multiple processes. And then the process could go back to, all I really need to think about is my little set of what I need to get done, and somebody else will take care of the complicated part of coordinating for me. So that's step 1. The next step, okay, so the Burroughs B5000 in the early 1960s introduced a concept at the time called descriptors, where a chunk of memory, so now you have multiple processes, a chunk of memory could be tagged that it belonged to a particular process so that you wouldn't have a bunch of different processes all accessing the same chunk of memory. And it wasn't just relying on the kernel to control that, it was also providing a complete restriction that a process couldn't access any region of memory that wasn't its own region of memory, including it couldn't access any region of memory owned by the kernel. It originally called descriptors. Very soon after, someone published a paper that introduced the term capabilities. And it didn't just say which process owned the region of memory. It would say whether the region of memory was executable or data. So you couldn't accidentally execute data, which is actually one of the causes of memory flaws in modern C programs. And it also included things like bounds checking, so tagged in the memory region, so you couldn't like accidentally go out of bounds from that memory region that belongs to that process for that object. At the same time, not too long after, there was a separate set of experimentation going on how to isolate those processes securely. So capabilities, that's the origin of containers. It really did start in the early 1960s. I'll trace it through. The M4444X experimental machine is the beginning of virtual machines. It actually started a few years later. This was a different approach to memory isolation, and it didn't have the same fine-grained level of control. It's pretty high level. So they called this a virtual machine, but all it really was a form of virtual memory. And this idea was that, well, if you had virtual memory, then your process wouldn't actually know about any of the other memory outside. So it would just sort of like get this address translation, and it would think it was in this world of here's the memory that exists on the machine, but actually there was a lot more memory out there that it didn't know about. This has been more or less successful over the years at providing, but it was a different idea of how to provide secure isolation for that memory. IBM then took the idea further, started improving on that. So I would not call that M4444X an actual virtual machine, although they used the name. The CP40 CMS, the Control Program 40 Cambridge Monitor System, was the first real virtual machine. And then they had another version a few years later for a different version of the hardware. Ironically, they didn't call it a virtual machine at first. They called it a pseudo machine. And then they thought that virtual machine name from the other IBM project, they're both IBM projects, was pretty cool. So they started calling their thing a virtual machine. All right, in the 70s, you have a little more advanced development of virtual machines. The VM370 for IBM System 370 took the idea even further. It really started locking down process isolation and things like that. But at the same time, the Plessey System 250 was a real-world telephone switch that was completely implemented hardware and OS using capabilities, not virtualization at all, because they wanted tight isolation between the processes on their telephone switch. The Cambridge CAP computer, developed at the University of Cambridge, was another one. It was implemented from the ground up, hardware and software, as a capability machine. It's actually still sitting in the lobby of the University of Cambridge Computer Lab, so you can go and see it there. Another thing in the 70s was Troot, which people actually, so you'll often see in papers or blog posts or whatever, you'll see people saying that Troot is the beginning of containers. It kind of is. It had sort of like file system namespaces, but it didn't have that process isolation of capabilities, which is actually part of modern containers. So it's more accurate to say that containers started in the early 1960s with capabilities. So in the 1980s, both virtual machines and containers pretty much completely died off. There were some good reasons for that. Kind of the whole idea of how computing was done started to change. The reason both virtual machines and capabilities were started was for these massive time-sharing systems, where you would have people sort of logging in remotely to these big servers, and they wanted to do time-sharing on the servers for multiple users. But that, in the 80s, it all completely switched to the users were sitting at PCs, like personal computers, and they would talk to a remote machine, but they weren't directly logging into the remote machine. It was a little more separated. And so they decided, well, we don't really need all this process isolation stuff on the big server because, we don't have multiple users on that. They're on separate machines, so the separate machines will provide the secure isolation. And the one big monolithic machine, it just runs one thing at a time, so it's fine. There's some other reasons for that. So, little known fact, because Intel has entirely buried it, in the late 70s and early 80s, Intel bet the farm on a new architecture. It's going to be the next big thing. It was the IAPX 432 architecture. It was a capability-based system, and it was going to be amazing. It was going to rock the world. They neglected to take performance into account. They really didn't work on performance at all. Didn't make it a priority. It was all about memory safety, which is good. But when it hit the market, there was a paper that did measurements at the time. It was up to 95 times slower than existing machines out on the market at the time. And it was a commercial flop. Totally failed. No one would buy it. So they had this funny little 8086 sort of in the back garage that they weren't really planning on investing in. It was who cares about it? That's just a boring side architecture. And they're like, okay, quick, this was a flop. What do we do? So they suddenly shoved the 8086 architecture into the front line, and that is the very first x86 machine, which is what we know now as pretty much the most ubiquitous hardware architecture on the planet. But learning that lesson that memory safety is slow, they took no efforts whatsoever with memory safety in the x86 architecture, which kind of led to the Spectre and Meltdown vulnerabilities because nobody was willing to think about or put any features in the hardware for memory safety. And sure, IPX 432 was a bit much, and they should have thought about performance, but from what I can tell, they just ran scared from any idea of memory safety at that point and never looked back. You can imagine these conversations happening in like the R&D department where somebody's like, I have this great idea for memory safety, and their manager's like, no, don't say anything about, don't mention the word memory safety, we don't want to hear it, just kill that, go work on something else, go. And that happened for decades. So IBM also had a capabilities architecture, the System 38. Didn't really go very far. It wasn't like a massive colossal flop like Intel's, but it didn't really take off. And there was another trend at the time, which is the sort of restricted instruction set computers versus complex instruction set computers. The x86 is complex. RISC is, you will see, actually there's a modern RISC architecture, RISC-V, that I'll mention later, but it's sort of, ARM is also a RISC, so it's restricted. So making your instruction set in the hardware much simpler to make it more performant, more secure, easier to control, things like that. So this was a trend that also started in the 80s. And the capability systems were definitely complex instruction sets. So like that trend of, well, maybe we should go to something a little bit simpler is part of what started, sort of pushed them out. So in the 90s, capabilities in virtual machines still pretty much dead. You did see things like virtual machines used for DOS on OS/2 or DOS on Windows. There's some limited use in the early 90s, but not much. The Linux kernel started in the early 90s. And then in the mid-90s, so there was this draft POSIX spec that was never actually approved, POSIX 1E, which included capabilities and access control lists. It wasn't exactly the capabilities from the 60s. It was sort of a little more limited, but it did have some of those memory protection features involved. And even though it was never officially approved, it was merged into the Linux kernel in the late 90s as capabilities. So there has, for a very long time, been this capabilities feature in the Linux kernel, which is, I would say, evolved from those early capability machines and the memory protection features that they had. Also in the late 1990s, there was this project called Disco, which is, they introduced the term paravirtualization. So some researchers at Stanford were thinking about how do we get existing operating systems to run on NUMA architectures with, say, tens to hundreds of CPUs without modifying them extensively. And they thought, hey, there's this idea back from the 60s, these virtual machines that let you run an OS on another OS. I wonder if that would be useful. So they wrote this prototype called Disco, published a paper on it, and a year later, those same researchers started a company called VMware to commercialize their concept of reviving virtual machines and making them commercially useful. Initially, it was only a workstation version for like running Linux on Windows or Mac or vice versa. Next decade, Web 2.0 brought the idea of making things smaller and lighter. So instead of having like one monolithic server, you might want to have a bunch of tiny little processes, tiny little like services running, and dedicating a whole machine to each tiny little service didn't really make sense. So that kind of drove some of the adoption and interest of reviving virtual machines. Jails was a FreeBSD feature to isolate, it was like a step beyond true. So it wasn't just file system isolation, it also did like process isolation, and it was a little bit farther along. And then there were two patch sets to Linux that never merged into the Linux kernel, but they also experimented with isolating processes running on a kernel. So this is not virtualization, but containers. They didn't call them containers yet. Denali it never took off very much, but it was an experimental VM. It was actually a lot more lightweight than most VMs that you would have today. It was a little bit closer to containers, but it did use virtualization or partial virtualization. QEMU was not originally virtualization at all. It was just an emulator, but I mention it because it became a virtual machine later. And then Zen is the big famous, that was kind of when virtual machines really kicked off in the 2000s and really got big. And one of its big unique contributions was the idea of multi-tenancy as a business. So you're not just, so you might actually have all these little lightweight services running, but you're not just buying hardware and running them on this hardware that you bought. You can actually have somebody who buys whole data centers and then rents out virtual machines to other people for money. Yeah, now it seems obvious, but at the time it was like a really crazy idea. And then Solaris Zones, like FreeBSD jails, but again, a little bit further, was another approach to isolating a process on a kernel. And that was the first time the word containers was used. Although they didn't actually call their project containers, they called it zones, and then containers was the business name. The 2000s, we have, I'm just gonna check time, all right. That crazy idea of Zen that you might wanna like rent out like some VMs from some hardware you own. Amazon really did it in a big way in 2006. They used the word cloud, but it's basically just VMs. And then around the same time, Linux added some more namespaces features that it didn't have before to start isolating not just file system namespaces, which they already had, and not just capabilities, but these namespaces were process IDs, IPC, network stack. So it made it easier and easier to isolate a process without having to go to virtualization. You know, you're gradually getting that same level of containment, but just for a process running on a kernel without using virtualization. A little later, we're getting towards the late 2000s now. Intel and AMD realized that virtualization was becoming big, but their hardware couldn't support it. So they added hardware virtualization features into the x86 architectures in Intel and AMD in slightly different ways. And then KVM gave the Linux kernel an interface to that. You kind of get the sense that there's this like co-evolution between containers and VMs, like all the way from the beginning. They're sort of back and forth and in and out. Google Borg. So the thing about that x86 hardware with hardware virtualization is it was really expensive. And Google had huge sets of hardware that they just didn't want to like replace with more expensive hardware. So they invented this other approach. They called it Borg. And it used all of these Linux isolation features, process IDs, IPC, network, file system isolation capabilities, to provide the same kind of virtualization that you would get, or the same kind of isolation that you would get from hardware virtualization without going that far. And because of that, they developed another feature for the Linux kernel called cgroups that also constrains what resources you can use. So it limits your memory usage and process usage, things like that, down. And then LXC was a container implementation in the Linux kernel that used all of these same features to provide this isolated OS image that didn't use virtualization again. The 2010s, we saw OpenStack. It's an open source cloud implementation, kind of like Amazon Web Services. And then Docker, which initially used LXC, but then forked off and implemented their own. And Linux added this feature called user namespaces. It's all the same namespaces that they had before, but you didn't have to be root to use them. So that meant Docker no longer had to run as root, which was one of the big sources of vulnerabilities in the beginning. Kubernetes came along. It was actually just Borg. It was Google's Borg, but they re-implemented it to release as open source. And it just does orchestration of those containers. Another interesting one here is Kata containers. So it's kind of weird because it's actually virtual machines. But it's virtual machines wrapped around containers to try to make them more secure, under the theory that virtual machines are more secure than containers. which isn't actually necessarily a good theory, in fact. And then there was some other work. So the general idea is people think that virtual machines are secure and containers are fast, but UKVM and LightVM are some projects just in the past few years that show that actually virtual machines can be every bit as fast or faster than containers with a few intelligent changes. And the very last set of things is capabilities have been coming back. You'll see, so FreeBSD added capabilities, and they weren't POSIX capabilities. They were this project called Capsicum that revived the memory protection of the early days. It's much more secure than Linux capabilities. So that's kind of interesting to see the old ideas come back again. Cherry is a hardware project, also at the University of Cambridge, that uses capabilities as a low level for secure isolation. I'll mention RISC-V because one of the interesting things about RISC-V is all those speculative execution vulnerabilities, Spectre, Meltdown, like they're really scary. RISC-V doesn't do speculative memory access. So it pretty much just excludes all of those vulnerabilities right off the bat. Google is making an OS called Fuchsia that's based on capabilities, again, memory protection coming back. And I won't go into the Spectre, Meltdown, and Foreshadow, because I already did, but they are one of the scariest things of our time. OpenBSD has some different features, Pledge and Unveil, that provide different kinds of isolation that are really interesting. They could be used for containers on BSD, which would be slightly different than containers on Linux. And then OpenTitan is another Google project providing a hardware root of trust that they're thinking may be implemented on RISC-V. So let's see. So there's some interesting developments now that kind of lead toward the future. So a few thoughts from all of that. One is that these like Spectre and Meltdown vulnerabilities, so they rip right through both virtual machines and containers. So all that belief that virtual machines are more secure and containers aren't, it's kind of meaningless now because all those assumptions that we've had over the past decades have been completely reset. So we get to start over and decide how to make these things secure. Containers have the advantage of modularity. Their security features are not monolithic, hard-baked. They are a set of modules that you add on or swap in from different operating systems, which means if you want to experiment with a new secure isolation feature, you can just add it onto your container. And it's like, you know, new Linux kernel module, let's just use that as well as namespaces and C groups. And so it has some potential there. Back on memory safety is boring and tedious. And it doesn't guarantee that your program is going to be secure, but it is kind of one of those maintenance things that everybody should do. So if you're in C, explore some of those libraries that make C more secure. And then also, sort of the last thing, when I say party like it's 1960, I don't mean wear bell bottoms and rainbow stripes. What I mean is, what was really interesting about the 1960s is we were just starting out in this whole range of hardware and kernel and operating system and like application workloads and the way they work together. And with Spectre and Meltdown, we are back there again, which is a little bit scary, but it's also a little bit exciting. So re-examine the full stack, and don't be afraid to question your assumptions. And I think we don't have time for questions, so come and catch me afterwards.
Okay. Thank you for the fascinating talk, and a warm hand of applause, please.